So in the talk of today, I will speak about topology of real algebraic hypersurfaces. Let me start with some introduction and motivation. So in this talk, X will be a real algebraic variety, so an algebraic variety defined over R. It will always be smooth and projective. Now we denote by X of C the set of smooth points, of complex points, sorry. Complex points of X, and by X of R, the real points. And I will always assume that the set of real points of X is non-empty. So X is equipped in this talk. So let L is equipped with an ample line bundle. Let L be an ample line bundle on X, also defined over R. And I will study the hypersurfaces in the linear system defined by L. So L are the hypersurfaces defined by real sections of L. So inside this linear system, there is the so-called discriminant that I will denote by delta. Which is the set of hypersurfaces which are singular. So if L, let's say, is very ample by Bertini, this is an algebraic hypersurfaces. And it's a real hypersurfaces inside L, so the complement is not connected. And say, let's say the spirit of Hilbert's 16 problem is try to give a list of the connected component of the complement of the discriminant. So let's say a general and modern version of Hilbert's 16 problem. Is to describe the complement of the discriminant. Say, give a list of all the possible topology of the real locus of hypersurfaces defined by L. Maybe I should use this. No. And we know that this problem is solved in very few cases, in very low degree. And one of the reasons why this problem is very difficult is for also numerical reason. It's a result of Kharlamov and Revkov. For the projective space, or in general for toric varieties, if we look at the number of connected components of the complement of the discriminant as a function of d, then this number of connected components grows very fast with d, grows super exponential in d. So it's very hard to try to find a solution for very large degrees. And the point of view I want to adopt it today in this talk is not try to describe explicitly the connected components of these complements, but to adopt a more metric or measure theory point of view and try to describe the measure, the volume of some interesting connected component chamber. So we will equip the linear system with a natural measure, and we will estimate the volume of some connected component. And more precisely today, I will show that the volume occupied by hypersurfaces with large Betti numbers for example, maximal hypersurfaces. So this volume is very small, is exponentially small.
Before you said the number is double exponential, then this volume decreases like...
It's very small. This volume will decrease exponentially with the degree. Even if, for example, the number of curves, of maximal curves, the number of connected components grows exponentially in the degree. There are many chambers, but the volume occupied by these chambers is actually very small. So this is very briefly the introduction. So I will start by describe the measure I will use for the linear system. Then I will state a more precise result. So and then I will give the proof of the main result. So I actually said I will be interested when the degree grows, so I will actually construct measures of tensor powers of L. So how one can construct measure in some linear system. So the goal, so let H0 XL be the space of global sections defined over R. I will equip this vector space with a scalar product. And then once we have real vector spaces together with a scalar product, this induces a Fubini-Studi measure on the projectivization of these vector spaces. And this projectivization is nothing but the linear system L. So the goal is to equip these vector spaces with a natural scalar product. And there is one standard way to do this is to fix some Hermitian metric on L. So So we fix on L an Hermitian metric with positive curvature. By this, I mean two stuff. So first, H is an Hermitian metric in the sense of complex geometry, of differential complex geometry. So on the holomorphic line bundle associated with L. And I ask this Hermitian metric to be compatible with the real structures.
But it doesn't need to be holomorphic.
Sorry?
The metric does not need to be holomorphic.
No, actually there is no, a metric cannot be holomorphic in any case. It can be a real analytic, but I'm only asking that it is smooth. And this is for the Hermitian metric on a algebraic line bundle defined over R. And for positive curvature, this means that the curvature of the Hermitian metric is a Kähler form. So we know that a line bundle has a first Chern class, and once we fix an Hermitian metric, we actually have canonically a representative of the first Chern class. So a Derham or Dolbeau representative of C1 of L. And the ample line bundles are precisely characterized as the line bundles that admits an Hermitian metric with positive curvature, is the theorem by Kodaira. So once we have this, once you have an Hermitian metric on L, we actually have an Hermitian metric on all the tensor powers. And now for any pair of global sections, we can consider the pointwise value of the Hermitian product given by the Hermitian metric. This is a function, this is a number that depends on x, so it's a function that we can integrate over the set of complex points. And this defines a scalar product, which by nature it's an L2 scalar product. So again, this I repeat. So the end of the story is that the choice of an Hermitian metric automatically gives us a scalar product, and then a Fubini study measure which we normalize so that total volume equals 1. So this is the space of measure space of probability that I consider. So maybe two remarks, especially for people that follow the mini curse of Antonio. So the first is that the scalar product on a vector space induces a probability measure on the space on the linear system. But also induces a Gaussian measure on the vector space itself. So we have the Lebesgue measure induces by the scalar product, which we can multiply by some exponential weight so that the total mass is finite. And then we can normalize so that the total mass equals 1. And if we take a section here with respect to this probability measure, so maybe and then we consider the zero locus. Then this is the same as if we take a random hypersurface with respect to this probability measure. So maybe what I'm saying is that the map that to any sections associate zero locus is such that the push forward measure, Gaussian measure, equal the Fubini study measure. So you can take directly a random hypersurface in the linear system, or take a random section, as I think you have seen in the mini curves, and consider the zero locus. And the second remark is more an example, maybe. Is when X is the projective space, the line bundle is the degree D line bundle on the projective space, and the Hermitian metric is the Fubini-Studi metric. So in this case, everything is very explicit. So of course, the space of global section can be identified with the space of homogeneous polynomials of degree D for this part. And the L2 scalar product induced by the Fubini-Studi metric is the one which makes the following basis. An orthonormal basis. And this is actually the only scalar product such that the standard monomials are orthogonal to each other, and which is invariant by the action of the orthogonal group in dimension n+1, which acts on the n+1 variables. And, these random polynomials with respect to this scalar product are called Costland polynomials. So this is sometimes called the Costland ensembles. Huh? No. No, so on R, they are the only scalar product which is ON plus 1 invariant and such that the monomials are orthogonal. And on C, this is the only scalar product which is unitary invariant without asking that the monomials are orthogonal. Are there any questions? Yes.
So, but in your case, you don't have a group action.
I don't have a group action.
To choose the measure for you.
No, I don't have a group action. No. Yes. So one natural way is to ask that everything is induced by an Hermitian metric by positive curvature, which is a natural assumption since the line bundle is ample. But yes, I cannot use this group invariance. Okay. So maybe let L of x as before, so an ample line bundle on a smooth real algebraic varieties. If we look, so as in introduction there, to the complex, to the holomorphic line bundle associated with X, then now the complex discriminant by Bertini is still an hypersurface, but it has real codimension too. So now this set is connected. And then this means that any two smooth complex hypersurfaces can be joined by a path of smooth hypersurfaces. And then by Ehresmann, this means that these hypersurfaces are isotopic. Are isotopic. Let's say the complex points. So this is by Ehresmann. So in particular, they have the same topology. The topology does not depend on the choice of the smooth hypersurface. On R, this is not true. But what we have a control of the topology of the real locus by the topology of the complex locus. So this is the Smith-Thom inequality. So if we take Z an hypersurface, now a real hypersurface, and let's say that we denote by n the dimension of the ambient variety, then the total Betti number of the real locus is always smaller or equal than the total Betti number of the complex locus. And by what I've just said, this right-hand sign, this total Betti number of the complex locus, does not depend on the choice of Z. So this is just a number which only depends on D and on L. And this is actually an explicit number which has a nice asymptotics in D. So it grows like D power n, where n is the dimension of the ambient variety. There is a coefficient here. So this is an integer, is the total intersection of the Chern class, the top intersection of the Chern class. And there is some rest. This is actually polynomial LD. Any coefficient can be computed in terms of Chern classes. We will be interested in the first coefficient. The first result I want to present is the following. So we fix a positive real, A, and we look at the set of real algebraic hypersurfaces defined by L power D. Hypersurfaces that have, let's say, a I total Betti number. So almost the maximal with this correction here. And then the result is that the volume of the connected component of the discriminant represented by these hypersurfaces is exponentially small. So two remarks. The first is that when the ambient variety X has dimension 2, so for curves in surfaces, this result was proved by Gaillet-Velchanger. And the second is for the coastline ensemble. This was proved by Diatta and Lerario. So this result is actually a consequence of a more precise result. Which is an approximation result as follows. So take an even integer, and we look at the following set inside the linear system. This is the set of degree D hypersurfaces such that one can find a degree D minus K hypersurface with the following property. The real locus of Z is isotopic to the real locus of Z prime. And the result is that from a measure point of view, almost all the hypersurfaces share this property. Meaning that up to an exponentially small term, almost all the degree d hypersurfaces can be approximated by a degree d minus k hypersurface.
What do you mean isotopic if they are in different spaces?
No, they live in the real locus. The real locus of z and z prime, they live in the real locus of x. So inside the real locus of x, there is an isotopy which maps.
Do you suppose that the dimension of the real locus is the same as the dimension of the complex, right?
Yes, because I'm supposing that everything is smooth. So this implies that they, yes.
Isotopic actually means lies in a small tubular neighborhood, or
No, there exists a
you're thinking about a long isotopy. Oh, it's an approximation.
They are very close. Yes, they are very close. Yes, they are very close. Like the real loci are very close in this sense. Yes. So a couple of remarks. The first one is that for the coastal ensemble, this was proved in the same paper by Diattel and Rario. So the second one is kind of easy remark, but this is a real phenomenon. Meaning that the complex loci of z and z prime have nothing in common. They are not isotopic, and in general, they are even non-diffeomorphic. They have different Betti numbers. And the third remark is that this theorem 2 implies theorem 1. So imagine there is a 1 close to this theorem. So this is kind of almost a formal consequence. So indeed, let's prove theorem 1 using theorem 2. So we take an hypersurface in degree d, and outside a set of small measure, this total Betti number will be the same as the total Betti number of an hypersurface of smaller degree. Then we use midterm inequality for z prime. And then so again, we have a formula for this total Betti number. And this is just a game. We have to choose the right k, which works for the a we are fixing in theorem 1. So in the remaining part of the talk, no, if you want to prove to theorem 1, we have to fix some a and prove this result. So let's fix some one a once for all. And what I'm saying is that then we can, theorem 2 works for any k. If we choose k large enough with respect to a as a function of a, then we have this inequality. That's what I'm saying. Essentially, by the formula over there, this is more or less, so there is this coefficient. And this is degree d minus k. So you see there is the main term is exactly in D. The main term is the main term of a degree D hypersurface. And if we take k large enough, the term of order n minus 1 will be smaller and smaller. Are there other questions?
What does it mean if you say if you choose k enough, but you fix k?
No. So sorry, maybe it's not clear. I just want to show that if we assume theorem 2, then as a corollary we have theorem 1. So we have to prove theorem 1. So we have to fix some a and prove this estimate. And then we can, so A is fixed, one for all, and then we can use theorem 2, which says that we can use any k. And then there is some large k which works. And essentially this is the proof. Other questions? Yes.
So, can you actually do fraction of d, or it has to be d minus k?
No, you can put here you can put actually epsilon d with epsilon positive. The proof is just a bit more involved, so I will only show d minus k for today, but you can put a fraction of d.
d to 1/2 plus epsilon?
No, I cannot do this on x. No. So the proof relies on some L2 theory of Ormander and Bergman-Kernez theory. So the general idea, the first big step, is to define a linear map A is approximation, from the space of global sections in degree D to the space of global section in degree D minus K. And then we want to justify the fact that we call this an approximation map. That is, we will show that outside a small set, so a set with exponential small measure, the real locus of Z of S is isotopic to the real locus of the zero set of A of S.
I do not understand the meaning of this. Outside of a small set, the topology is destroyed completely, and then you are saying that there
No, sorry, meaning a set in the space of global sections.
Okay.
Of so small meaning the small measure.
And after you delete small set,
So outside an exponentially small set, outside this exponentially small set, we can find a degree d minus k hypersurface whose real locus is the same as the real locus of a degree d globally.
not outside.
Globally. So of course it's very important to remove some set because it's not true in general. But from a measure theory point of view, these sets that we remove are very small. So this is the general idea. So I will give some details. So the first step is the following. Let's say for any even k, so large enough actually, there exists a real global sections of degree k such that the zero locus is smooth. Okay, this is just Bertini. There's nothing more than Bertini. And the second part is that the real locus is empty. Okay. So this is very easy. So one take M large enough so that L power M is very ample. And then this sigma is just a small perturbation of the sum of the square of a basis. So this is empty real locus. Maybe it's not smooth. We just perturb this section to have a smooth complex locus. And so from now we will fix some k to prove the theorem. And for such a k, we fix such a global section with empty real locus. Sorry?
How is M related with
Sorry. K is just 2m.
So it's not really any. Large enough. Okay.
Yes. So we fix some sigma, and when we fix some sigma, we have naturally the following subspace of the space of global sections. This is the space of global sections, which vanishes along the zero locus of sigma. Which is the same So maybe a small abuse of notations, as the subspace of the global section of LD, which once want to denote by a sigma tensor H0 of LD minus K. And so recall that the space of global section is equipped with an L2 scalar product. So of course, one we has a subspace, one also has an L2 orthogonal decomposition of the space of global sections, so that any section S, global section, can be written as sigma times something in degree D minus K, that we want to call A of S, plus some orthogonal part. So this formula defines the map A. So now there is the, let's say, the key point. So we'll consider global section in this orthogonal part. So the section of the form S orthogonal. So such a section is an exponentially small C1 norm along X of R. So we are looking to the real part of this section. L is equipped with some Hermitian metric, so it makes sense to speak about C1 norm. And so the claim here is that this norm along X of R is very small, provided that the section lives in this orthogonal part. And the proof of this claim is by using this Bergman kernel theory. So I can maybe give an idea of what is happening. So we have the real locus of X, and disjoint from the real locus of X there is the zero locus of sigma. So maybe I wrote something like this. And actually the precise statement is that almost all the C1 norm of a section tau is concentrated in a very small neighborhood of Z of sigma. So small is so one can be precise. So there is this a very natural scale, let's say in Keller geometry is 1 over square root of d. And this section tau looks like some Gaussian functions along the zero locus of sigma. And as by construction the zero locus of sigma is disjoint from the real locus of x, this section tau will have a very small norm along the real locus of x of r. And more precisely, are there maybe it's a bit? Are there questions about this point 3? Yes. So the idea it can be made more clear. So the okay. Let's skip to point 4 for one moment. Just the end of the proof is almost done. So let's assume this point 3 for 1 minute. Then what's happening is that the section of the form S orthogonal over there is exponentially small C1 norm along x of r. So along x of r, S and the sigma tensor A of S, they are small C1 perturbation of each other's. So by Tommy-Sotopi lemma, if the C1 norm of S is big enough, we know that C1 small perturbation doesn't change the topology. So provide that S vanishes the C1 norm of S is big enough. And that's where this small set appears. So this is exactly the small set, the set of sections which does not vanish, which does not have C1 norm big enough. So this is the same as the following property: S is far enough from the discriminant. So there is a tubular neighborhood of the discriminant where the sections do not have large enough C1 norm. on the discriminant, they are singular, and just close to the discriminant, they do not vanish. Transversally, like with some large transversality. So there is, maybe I change color. There is some tubular neighborhood of the discriminant that we want to avoid.
Discriminant is singular, no?
Yes, so it's the space of a section whose distances is smaller or equal than some epsilon.
It's not tubular, just neighbor.
Yes.
Don't say tubular.
Topology doesn't change when you are inside.
So if you are outside of this UD, what one can prove is that S and sigma tensor A of S are in the same connected component of the discriminant. Yes, one can prove this. And this is actually because this vector over here is just S orthogonal, which has a very small C1 norm. This is exactly represented by these neighborhoods S orthogonal. So if you are close to discriminant, it may happen that you cross the wall. If you are far from this discriminant, you are sure that S and sigma tensor AS share the same topology. And so the result is just by computing this volume of the tubular neighborhood. And this is the small set of sections that appears in the theorem. So I will stop here. I'm already late. Sorry. Thank you.